This is a solution guide to your nuclear chemistry practice problems. Problem 1 asked us to write balanced nuclear equations for each of the following processes. For the first one, we need beta decay of vanadium-55. So you start with your only reactant being the vanadium-55, which is about to undergo decay. We know that one of the decay products has to be a beta particle, and a beta particle has the symbol 0 - 1e. Now we have to follow our rules for writing nuclear equations, that the sum of all the numbers on top has to be the same on both sides, and the sum of the numbers on the bottom has to be the same on both sides. Since the vanadium-55 has a mass number of 55, 0 plus 55 is going to work here. On the bottom, vanadium has an atomic number of 23, so 23 is equal to -1 plus 24. And lastly, you look up element number 24 on the periodic table and find out that it's chromium. The next one wants alpha decay of curium-244. Our alpha particle is a 4,2 helium. And now we just need to find our missing numbers. 244 is equal to 4 plus 240. 96 is equal to 2 plus 94. And when you look up element 94 on the periodic table, you find out that it's plutonium. And our last one is an example of positron emission. You start with iridium-192, and a positron has the nuclear symbol 0, 1e. And now we have to work on our numbers. 192 is equal to 0 plus 192, and 77 is equal to 1 plus 76. Element 76 on the periodic table is osmium. The thing to notice about all these equations is that they're all decay processes. In every case, they start with one item on the reactant side of the equation, and it falls apart into a decay particle, a beta, an alpha, or a positron, plus a new daughter nuclide that's made after that decay particle is given off. Question number 2 asks us to predict what type of decay will occur and then write the balanced nuclear equation for that process. The key here is to start out by figuring out how many protons and how many neutrons each of the original nuclides has. So our cadmium-118, when I use my periodic table, I find out it has an atomic number of 48, and when I do 118 minus 48, I find out that this has 70 neutrons. Doing the same thing to my other nuclides, tin ends up having 50 protons and 60 neutrons, and my astatine ends up having 85 protons and 129 neutrons. Because our chart of stable nuclides is plotted with neutrons on the y-axis and protons on the x-axis, I have to know how many protons and neutrons these things have before I can look at where they're located on the chart of stable nuclides. Remember, we do not plot the mass number on this chart. We plot the number of neutrons. Next, I'm going to put a dot on my chart of stable nuclides to represent each of these nuclides. My cadmium is this little blue dot right here. My astatine is my red dot way up here. And my tin is a little green dot right there, and I'm going to put a highlighter dot over the top of that just so you can see it a little bit better. There's the green one right there. Now, based on the location of these dots on our chart of stable nuclides, I can predict what type of radioactive decay they're going to undergo. The cadmium is located right here, which is slightly up and to the left of the diagonal cluster of dots, so my cadmium is going to undergo beta decay. So the first particle in my cadmium equation is going to be a beta particle. My tin is right here. That's down and slightly to the right of the cluster of stable nuclides. So that one is expected to undergo positron decay. And my astatine is way up here. It's simply too large, so I expect that one to undergo alpha decay. Now that I've identified what type of decay each of these is going to undergo, I have to find the remaining missing particle. For this, we just use our rules of nuclear equations. 118 is equal to 0 plus 118, and 48 is equal to negative 1 plus 49. Element 49 is indium. For my tin, 110 is equal to 0 plus 110, and 50 is equal to 1 plus 49. Element 49 is again indium, although this is a different isotope of indium than what I had before. Lastly, the astatine. 214 is equal to 4 plus 210. 85 is equal to 2 plus 83, and element 83 on the periodic table is bismuth. For question number 3, we have to fill in the missing particle and then decide if each of these qualify as nuclear decay, nuclear fission, or nuclear fusion. Although these aren't exactly the same as our nuclear decay equations, the same rules are still going to apply here. We're still going to make the sum of the top numbers the same on both sides and the sum of the bottom numbers the same on both sides. So here we start with a 231, and that's equal to 192 plus 39. And 91 is equal to 77 plus 14. And element 14 on the periodic table is silicon. We can do the same process in reverse if we need to know what particle we started with. Here we have something that has come apart to become polonium-210 and a beta particle. To figure out where I started, I'm just going to use my rules of nuclear equations. 0 plus 210 is 210, and negative 1 plus 84 is 83, and element 83 is bismuth. And lastly, I have to figure out what I get if I combine beryllium-9 with carbon-12. So I'm going to do 9 plus 12 to get my top number, and that's 21, and 4 plus 6 to get my bottom number, which is 10. Element 10 on the periodic table is neon. Now I look back and decide what each of these represent. This first one is one nuclide coming apart into two smaller ones, and that's our definition of nuclear fission. This one here is one nuclide coming apart into two smaller ones, but one of those smaller nuclides right here is one of our radioactive decay particles. That's a beta particle, and when one of your pieces is one of our radioactive decay particles, we recognize that that's a nuclear decay, a radioactive element decaying to form something new. Our last one, we have two small elements coming together to form a bigger one, and that's our definition of nuclear fusion. Question 4 is to create a decay chain. So what we're going to do here is try to put together a series of equations to get from polonium-213 to bismuth-209. I'm going to use the chart on page 5 of my notes because I can really see what's going on there. This star represents my starting point of my polonium-213. Because of where polonium-213 is located, I know that this is going to be an alpha emitter. So I start by writing an equation for the emission of an alpha particle from a polonium-213. So 213 is equal to 4 plus 209, and 84 is equal to 2 plus 82. That creates 209, 82 lead. So now I have moved down to and over to right here in my first step of my decay chain. But the 209 lead created here is still unstable and is another version of a radioactive nuclide. But I need to get to where the smiley face is, which is really down one and to the right, which represents the loss of a neutron and the gain of a proton. The radioactive decay that represents trading a neutron for a proton is beta decay. So my second equation in this string is 20982 lead emits a beta particle to create 20983 bismuth, and I've made it to where I want to go. It is important here that the alpha decay occurs first and the beta decay occurs second, because from up here I was in the alpha region of my chart. And so the polonium is an alpha emitter, but from right here I can perform a beta emission and come down to where I need to be.